Okay. Selection configuration for this first one, the nitrogen. So if you just add up the electrons, the 2, the 2, the 3, you're at 7. So that's an easy way to make sure that you got the correct number of electrons in there. What's going to be the same about the sulfur's electron configuration?
Everything you've written above.
Close.
Oh.
1s2, 2s2, 2p, all that's the same. And then 6 here, and then what? 3p4? 1, 2, 3, 4. Yeah, 3p4. Oops, I didn't write 3. There we go. And what's going to be the same about the iron? More of the same, right? Just keep writing it and just keep going. So 1s2, 2s2, 2p, 6, 3s2, 3p6, 4s2, 3d, 2, 3, 4, 5, 6. You good with that? Which one was Hund's rule?
Electrons fill the empty orbitals in the same sublevel
Before doubling up?
combining electrons in the same.
Okay, so let's say that I've got a p sublevel. How many orbitals are in that p sublevel? 3, right? It's the second sublevel. You go up by odd numbers, 1, 3, 5, 7. So, all right, I've got these 3 sublevels. If I have 2 electrons to put into it, or let's say 3 electrons like I did with the nitrogen, where do I put them? 1 in each. There's the crux of your Hund's rule. And I don't get a double up until I get to what? Oxygen, in this case. So once I've got a 4th electron, now I don't have any other choice. I have to start doubling up. So if I had oxygen, I'd put a 4th one in there. And how about Pauli's principle? They spin, right? And they spin because these things are charged particles. And when a charged particle spins, what does it create? Creates a magnetic field. So if I've got one spinning one direction and the other one spinning, oh, that's the same direction. The other one spinning the opposite direction, then I get a north pole here and a south pole here and a south pole here and a north pole here. And then if I'm looking at how they're attracted to each other and how they're not attracted to each other, they're pushing off here, right? Get away, get away. But with these guys, they're totally attracted to each other. I'm attracted to you, you. So I've got the poles pulling these electrons together, even though their charges are pushing away. And if the electrons were spinning both in the same direction, then they'd have norths on the top, negative charges, and souths on the bottom, and all 3 of those aspects would be pushing them away, and they wouldn't be able to last in the same orbital. They'd bump each other out. Okay. Heisenberg's uncertainty principle, which one was that? Say that again? They're too small to be seen. And what do we want to add to that? Sure. Too small to be seen because looking at it moves it. Does it have to move it very far? Because if you're zooming in close enough to see something that's the size of an atom, how big is your field of vision? Super tiny. Like, why does a sniper always have a second person sitting there next to them? The guy looking through the sniper scope sees just like a tiny little thing, right? And the guy with the goggles or the binoculars sees the whole field of vision and be like, oh, what are you seeing? Oh, I see a truck. All right, go left a little bit, and then you'll see the target kind of thing. So you do not have to move the atom very far for you not to be able to see it. Just picometers. You move it a picometer, and now it's not in your field of view anymore. What is the shorthand notation for an electron configuration? Have you go to the last noble gas? What's the significance of that last noble gas?
It's the last stable element.
Last stable element. What do you know about those electrons for that last noble gas?
They're filled up.
Filled up? Anything else you want to say about it? If chemistry is the actions of electrons, those particular electrons are off limits to do any chemistry. They cannot do a darn thing, so it doesn't matter. I only care about the electrons after that noble gas because those are the only electrons that can do anything. Noble gas configuration for titanium. So titanium, we got that 22, and so I back up to number 18. So I got Ti, and then in brackets, will put some argon, and then everything after argon is 4s2, 3d2. Energy level diagram for, somebody got a name for Y? I'm gonna try to pronounce that one. Yttrium, yeah. Super common element, right? Where it's so common, I'm looking for it. Oh, there it is right there, okay. So
Would it be 4S2 or does the D go before the S?
the 4 comes before the D.
Oh.
So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. Yeesh. So one line, one line, one line, one line, one line, 3 lines, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so up, down, up, down, up, 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 down, 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 up, down, up, 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 down, 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 up, down, up, 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 down, 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 up, 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 down, 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 up, down, up. Nope. Bad. Up. We good with that?
Yeah.
Did you double it up?
Yes, I did.
So
You know,
you've violated which rule?
Paul, I don't know how to pronounce his name, his principal.
Nope. Hans.
Yeah, the person.
How do we know, what's a quick, easy way if you just were given the diagram to know that you're looking at yttrium?
Count.
Go to that last one up there, right? Go to 4D, find 4D on the periodic table, and slide over 2 elements. So, oh goodness, I'm totally wrong. It's the first one. The second one's zirconium. My bad. There's only should be 1 electron there. Yeah. And then the other way is you could just count, right? 2, 4, 6, 8, 10, 12 until you got up to I don't know, what is that, 39? Yeah. All right.